Whenever you're ready.
All right. Well, we math students are always ready for anything. So, starting off, we have this nice equation here. Y double prime minus 2y prime plus 2y equals x cosine x. And now, to use what method we're going to use to solve this is something called inverse operators. This is really, really helpful and it's really critical in differential equations. You're going to use this a ton. So first off, we're going to actually rewrite this equation, but with a slight difference. We got y double prime minus 2y prime plus 2y equals x times e to the ix. Now, why are we going to do that? Well, there's a little theorem about differential operators called the exponential shift theorem that we can only use with an exponential term. So we can change this cosine into e to the ix, and then later in the solution, we're just going to omit the imaginary part, and then we have our answer for cosine x. So I just rewrote it right here, as you can see, and now I'm going to rewrite the left-hand side in terms of differential operators. And that's just going to be d squared minus d plus 2, and that's operating on y. Now, we're going to take that operator, move it to the other side, and we have our inverse operator, which, scribble that out. D squared minus 2d plus 2 x e to the ix. Now, if you remember the exponential shift theorem, that's essentially it. For your exponential term, whatever the coefficient of the exponent is, that is going to be the coefficient that you're going to add to every d term in the inverse operator. And you'll notice our coefficient is I. So now I'm going to rewrite this as in our exponential shift form, where we have the e to the ix out of the operator, but then we rewrite this. D plus I squared minus 2 times D plus I plus 2. All of that in parentheses. And that's going to be operating on x. So as you can see, I took the coefficient of the exponent and added it to our differential operator. And that's the exponential shift theorem. And now, with this, we're just going to FOIL that out and simplify it into terms that are really helpful for us, because we have one really helpful series expansion here. This is a little digression we're going to have. If you have something in the term of 1 over 1 minus x, you can actually rewrite that as 1 plus x squared, and on and on. So we're going to take our differential operator, expand that and simplify it, and after massaging it a little bit, it gets a little bit complicated, but it's not too bad, which I'll write out right here. And this term below the e to the ix, that is actually because when you want to turn the differential operator into this form, you're going to actually have to pull out this 1 minus 2i. And then our differential operator will turn into something a little bit complicated here, but if you just bear with me, you'll see it works out pretty well. And that's going to be over 5. So that's our differential operator, and that's going to be working on x. But as you can see in the theorem up here, we rewrite that. So now our differential operator, well, I'm going to rewrite this like this. This is our p to the negative 1 d of x. This is a symbol for our inverse operator operating on x. So I'm going to rewrite that now with this series expansion, which we have right there. And that's just going to equal 1 plus 2d, 3 plus I over 5. Now you might be wondering though, but if this is a series, why didn't I go up to the third term, or the fourth or the fifth, or whatever? Well, that's because if you think about it, you can only operate on x one time before it gets to 0. So any term with d squared or higher order is just going to be 0. So we can omit those. So really the only term we have to worry about is that right there. And now we take that and operate on x, and then we're going to multiply it by our coefficient up there, which leaves us with y equals 1/5 times e to the ix, parentheses, x plus 2xi plus 14 over 5i plus 2/5. And now we're almost there, but remember, we changed our cosine x into e to the ix. So now we have to actually take this term and then omit the imaginary part. And we're also going to add our complementary solution, which I can write over here real quick. That's going to be really easy. It's just going to be that's a complementary solution right there. That's a sine x right there. Sorry for it being messy. But yeah, now we just take that and add it down here. And so we're left with y equals c1 e to the x cosine x plus c2 e to the x sine x plus this term right there. And that'll be our final solution. And as you can see, what looked like a really, really messy differential equation is really simplified with differential operators and the exponential shift theorem. And as long as you just trudge through it and really pay attention, you realize that it's actually not too bad. And that's how we solve that equation using differential operators.